great for a class to have that kind of stuff. They basically built kind of a parallel line on a water pipe, and they had some little detectors you could move up and down. I think you use like to show the intensity, and it just brings the whole thing to life. Okay, we're ready to roll? All right. Okay, we're going to talk about SWR and how to measure it. Honestly, this is supposed to be a pretty introductory kind of thing, so I'm looking across the room and go, okay, you could give this presentation, you could give it. So, but I think I'll stick to kind of the basic thing here, and if we want to drill in a few places deeper, that's cool too. Okay, what's SWR? How do I measure it? My background, so I'm a double E. I've been in the test and measurement business for over 35 years. And I've actually written 2 books about different types of test equipment, so I do know a little bit about measuring electronics. A lot of times when I give this talk or something similar, I'll spend a bunch of time on the multimeter, because like everybody needs to have, well, every hand needs to have a multimeter. Everybody have one? I mean, seriously, all the basic measurements, for 30, 40 bucks, maybe not even that, you can get one fine meter. But the thing the multimeter does not do, it really doesn't help you with radio frequency measurements. And so when it comes to your antenna, you can make ohm meter measurements on your coax and stuff, but it's quite limited. And antennas are so important to us, right? They're the thing that goes from electrons flying down the cable to electrons, EM waves flying through the air. We gotta have a way of measuring our antenna system. And for the most part, that's an SWR meter or an antenna analyzer, or maybe one of these low-cost vector network analyzers. And so you need to get a multimeter if you don't have one, and you really need to think about getting some kind of SWR meter or maybe an antenna. You just don't know what's going on with your antenna unless you have a way of measuring it. Okay, what is SWR? Standing wave ratio. The slightly more accurate, proper term is voltage standing wave ratio, so sometimes you'll hear people call it VSWR. Especially if they're from Texas, they call it VSWR.
Well, those Texans are getting a hard
the basic idea is it measures the match between a source, usually for us that's the transmitter, and a load, the antenna. In fact, that's the only thing you get out of this presentation. That's the key bullet. Is I'm trying to figure out is my antenna, to what extent is my antenna matched to my transmitter? Good match means the signal flows well. Bad match means the signal flows not so well. And so really we're after maximum power transfer, and it goes both ways. Get more signal to the antenna, get more signal coming back from the antenna. You probably know some of this already. A perfect match with SWR is 1. So that's perfect. Anything greater than 1 is less than perfect. In fact, you can't have it less than 1. It's a ratio, so it's always greater than or equal to 1. This is something that always strikes me as kind of odd. For some reason, there's a tendency for people, particularly the FCC, the FCC question pool always talks about SWR as 1 to 1 or 2 to 1. Either with that kind of nomenclature, or they may even spell it out. I don't quite get it. It's just a ratio, so to me it's just a number. So I refer to it just as a number. But you will see that 1 to 1, 2 to 1, 5 to 1 kind of nomenclature. Pretty broad rules of thumb. So any SWR less than 2 is a pretty good match. If I'm tuning up an antenna, if the SWR is 1.5, I'm happy, I'm done. If it's much more than that, I might fiddle with it some more, but generally less than 2 is pretty good. Something over 3 is a poor match, and anything higher is a very, very poor match. Now, there might be some cases where that's okay, and we'll talk about that a little bit, but really we're focused on 50 ohm transmitters, 50 ohm transmission lines, 50 ohm antennas, so those things should all be well matched and have low SWR. So how does this look on the transmission line? It's all about forward voltage versus reflected voltage. So transceiver sends, when you transmit, the forward voltage goes down the line, some will get reflected and come back, and the actual calculation is here. You do V forward plus V reflected divided by V forward minus V reflected. But actually there's, I think I've got a better, yeah, Stu did some really cool graphics here, courtesy of hamradioschool.com, that makes it even better. Let's see, there's my transmission line. So here comes the forward voltage going down the line. And then if there's a mismatch, there will be a reflected signal. Now, if there's no mismatch, it'll all be absorbed by the antenna and hopefully radiated. But I'd say in most practical cases, you're going to get some kind of small mismatch. So you will get that reflection back down the line. And the reason this starts to become important is when those two signals meet in the middle, at the forward signal and the reflected signal, depending on the phase, they can either add together constructively or they can add together destructively. And so you get either an increase in voltage or a decrease in voltage. And so here, in this case, we're showing them as adding together. This graphic is not 100% accurate. We're just kind of looking at this one piece of the transmission line. But the basic idea is the forward and reflected voltages add together. So now I get a bigger voltage on that line. It actually does raise the voltage. And so now I'm going to park that, stick that over to the side, because that's our maximum voltage on the line when they add constructively. But there are other possibilities too. They can add destructively. So let's take a look at that. Okay, again, forward voltage going down the line, get a reflection coming back. Here we're showing them exactly out of phase. And so you're going to get this big sine wave and subtract off the smaller sine wave. So you'll get a voltage minimum there. So that'll end up being the smallest voltage on the transmission line. So go ahead and store that. So that's the min voltage. And you go, why are you telling me all this? It's because this is where the standing wave ratio comes from. It's the ratio of the max voltage and the min voltage. Simple calculation is the standing wave ratio. That's where the name comes from. That's the concept. Now, I think from a ham radio point of view, you may be, okay, it's interesting to know that there are these standing waves on the transmission line, but I think more what we care about is this concept of when I have a standing wave ratio like that, that means if it's not 1.0, that means I've got a mismatch on the line. That's what we really care about, is getting rid of that mismatch and having maximum signal transmitted to our antenna. Does that make sense? Questions on that? Okay, let's skip through that one. So one way to measure this is with an SWR meter. So what we do there is we have our transceiver, we have a short coax, stick the meter in line. I brought one of my meters. This one is something I bought at a swap fest years ago. It's fairly inexpensive. Probably only good to 30 megahertz DHF bands, but you can pass that around. Anyway, we'd stick our meter in line, and then we transmit with the transceiver to apply energy to the system. We create a forward voltage, reflected voltage, and our meter can tell us what's going on. It'll read out the SWR. So that's pretty common. The thing that's becoming more common, which is really nice, is the SWR meter is built into the transceiver. So who's got an SWR meter of some type? Okay, and who's got one built into their transceiver? Typically on HF, not your VHF, UHF radios, but I'd say most of the HF radios do that now. And that is really sweet. So now you just push the right buttons on your transceiver, you get an SWR measurement. Here's another SWR meter. This is a Diamond. Diamond has a series of these. It happens to read SWR and power. And typically the way these work is there's a cal position here on one of these switches that you transmit, you flip it to cal, and you turn that knob to get full scale on the meter. And then you flip it back to SWR, and the meter reads out the SWR. That's the mechanism to calibrate forward versus reflected voltage. So this thing's about $100, goes up to 200 megahertz, so you can cover up to 2 meters. And they got one so they go higher in frequency. Okay, some comments on SWR. So it's important to remember the meter is measuring the match at the point of insertion. Okay, so if I put the SWR meter here and I have 100 feet of coax to my antenna, I'm not really measuring the SWR at the antenna. I'm only measuring it right here. And so in general, it's better to be closer to if you're trying to figure out what the antenna is doing, you want to measure closer to the antenna. SWR does not indicate the effectiveness of your antenna at all. Because I can prove that to you, because if you have a dummy load will have an excellent SWR, but the dummy load's purpose in life is to not radiate. So it's just being a good 50 ohm load. So the SWR is going to tell you what the match is, but it may or may not actually be radiating. On the other hand, it does give us an idea of what's going on, right? So if I have a dipole up in the air and I'm measuring the SWR on it, and the SWR is looking pretty good, I can probably have confidence that, okay, it's probably connected up and actually radiating, but there's actually no guarantee of that. Yeah, when measuring or adjusting the antenna, put the SWR as close to the antenna as possible. Sometimes we can do that, sometimes we can't. Make sure the SWR meter is spec'd for the frequency of interest. Like I mentioned, this one probably only goes to HF, but that Diamond antenna goes to 200 megahertz, and particularly as you go higher in frequency, make sure you've got something spec'd, the meter spec'd to do that. Yeah, long lossy coax makes the SWR look better. This is kind of counterintuitive maybe, but anybody know why that is? Stu?
Because you're losing the reflected signal to heat as it goes down that long lossy line.
Yeah.
So you're not reading it as
transmit,
high as it is.
some amount of power down the antenna, get some kind of mismatch at the antenna, and by the time the signal comes back, if it's lossy, if the transmission line is lossy, you're going to get less and less signal as it comes back down. You go, oh, measure my SWR, it's forward compared to reflected, and all of a sudden it looks like the reflected is much smaller than it really is at the antenna. So that's something to watch for. And then maybe just a little bit about how low should the SWR be. Well, I always like to say, depends on the situation. What can be reasonably expected? Most of our antennas we put up for, say, 2 meters or 70 centimeters, those things are intended to be a good 50 ohm impedance. So my expectation is when I hook that up, I should see a pretty good match. Right? Maybe, again, certainly less than 2 to 1. I'd probably be looking for 1.5, SWR 1.5 or better. On the other hand, if I have a dipole up and I had originally cut the dipole for a certain frequency, say the high end of the 20 meter band, and I decided I'm going to actually transmit on the low end of the 20 meter band, I'm probably not in the sweet spot for that antenna. I'm probably off to the side a little bit, and the SWR is going to go up as I move down in frequency. And so, shouldn't surprise me if maybe the SWR is up to 2-to-1 or something like that. And if that happens, you know, I have a choice. It's like, is that okay? I'll just live with it. Maybe get an antenna tuner to help with it. But it's really what reasonably can you expect. There are cases, not going to go into it in any detail, there are cases where people basically run a dipole antenna with a very low loss feed line, usually a ladder line, and the whole idea is they'll operate that antenna at high SWR. They'll use it on all different frequencies, and they're counting on the low loss of the feed line to guarantee they still get a pretty good signal to that antenna. So that's a legitimate thing to do. So if those folks who were watching saw this slide, they would say, hey, wait a minute, it's okay, because I use open ladder line, and I do this, and I do that, and I still radiate well, and yeah, you can do that. So this, we're really focused on kind of the 50 ohm case. Okay, the other thing you can do is have an antenna analyzer. And so what these things are is they have like a little signal source in them, and they put a signal out their test port, and it goes to the antenna, and then whatever reflections are going to happen come back, and then the meter just reads the SWR of the antenna directly without involving your transmitter. And so, as you can imagine, that's extremely, extremely handy. And there are just a ton of these out there. This NFJ is pretty popular. You see a lot of those. This is some Japanese company I can't pronounce. I think it's Kyle in there?
Rig expert. No.
Kyle's got a rig expert out that he used to tune up Stu's antenna. I think it's still out there. You may want to take a look at that. And one of the claim to fame there is you get a nice LCD display that shows you a frequency sweep of your SWR. So now you can really start to see what's going on with your antenna, right? Because a lot of these, like the one I have here, just reads at one particular frequency, and you tune around, you sort of try and mentally put that picture together. So that's pretty sweet. These down here, this guy that's actually showing a Smith chart. Here's another one that has frequency sweep. There's actually an amazing number of antenna analyzers out there these days. Here's the MFJ 259B. I actually have one of these, but I left it at home. It's about $250. It covers up to 170 megahertz. You can measure lots of stuff. It'll do return loss, impedance, reactance. It does more than SWR.
It also measures loss and coax.
Yeah, it measures coax loss. I'm trying to remember how it does that. It's
If you put a short on the end of the cable, then the total round trip, then the reflection coefficient is a direct measure of the attenuation.
yeah. I think it actually you just leave it open. I think you get the
Yeah, this
reflection.
one.
That's what you're
Yeah.
I have a 100-foot spool of RG8 that I bought probably 40 years ago. And I put my analyzer on it, and it's so lossy I don't use it for anything.
Yeah.
It's pitiful. You know, if that old phone would deteriorate.
Yeah.
And I don't recommend buying old coax for anything.
especially if it gets wet.
If it gets wet, we've got another issue. Because you can put copper in the semiconductor will be oxidized.
Yeah. Few usage tips. Best accuracy near 50 ohms. So these things will start reading resistance and impedance values away from 50 ohms, but if it says 3,000 ohms, it's not terribly accurate. This is an MFJ 269.
It's higher frequency.
It goes to I gotta read it wrong.
UHF.
That's a
I
higher
know
dollar.
they keep making the font smaller.
High dollar model there.
Yeah, there is a UHF setting. Okay, yeah, so this one goes up and covers UHF. Can I pass this around, or? Thanks, Larry. Let's see, don't use in a high RF environment. I found that last night. I had an APRS transmitter going and kept throwing my SWR reading off because these things have broadband receivers in them. Input circuitry is sensitive. You can blow out the input pretty easily, so you discharge antennas before disconnecting. Do not apply voltages to those test ports. And then don't over-interpret the results. All the analyzer's doing is looking out the test port and trying to figure out if it's seeing 50 ohms or not. Just checking impedance match. Here's my favorite antenna analyzer. It's pretty simple, but it's pretty high quality. It's made by Comet. It does go to 500 megahertz, and it's a little more expensive. It's $430. That's what I have here. It's pretty simple in that it has an SWR reading and an ohms scale. You can read both of those simultaneously, but that's all you get. You don't get all these other little features. The other thing I have is a little VNA. It really is a network analyzer in a box. There's a ton of these out on the market too. This one was still fairly reasonably priced. You know, it's not a $30,000 network analyzer like Keysight builds, but $550 does a pretty good job. Goes up to 200 megahertz. This one connects up to a PC, and then you run software on a PC, and can give you a lot of flexibility. Not only can you do impedance and SWR measurements, you can actually measure filters. You can do through measurements with this thing. So that's what the software looks like. Again, you get the performance versus frequency kind of curve. And then here's some measurements I made. This was made on a 2-meter Yagi antenna. And let's see. This curve is SWR. You see it goes down to almost 1. Right? So its sweet spot is, what is that? That must be about 144 megahertz. So it's made for the low end of the 2-meter band. And then it goes up, and then this is actually return loss measurements. It's the same information displayed a little differently. The same measurement, I could say, okay, show me the impedance. So here's the magnitude of the impedance. You know, right in the middle where the SWR was good. We also saw 50 ohms. Okay, that makes sense. And then as you move up and down in frequency, you see the impedance coming up.
Bob, have you compared that VNA that you got for 550 against the regular iPhone?
Yeah, I have not.
200, 300 gram system?
No, I have not. I expected it to be actually quite good because, you know, it comes with a cal kit, right? You have to put a short, open, and load on. And if you think about it, particularly at high signal levels, when you do that inherently makes it a very accurate measurement. Yeah, I've never checked that out. Okay, so let's do a little demo. Let's see, could you help me with this demo? Okay, this is a vertical antenna. Anybody want to guess what band that's for? 70 centimeters is a good guess because that's a half wave. So this is a half wave radiator, and then this gizmo is the matching device that lets you feed it from the end.
What's that matching called?
What's
What
that?
kind of matching circuit is that?
I don't know. It's some kind of hairpin gizmo to match
Well, I've
it.
got a gamma match antenna. I hate it.
So I take this meter, and what we want, I mean, okay, it's vertical, so I'm going to use it on FM typically. So like the middle of our FM FM portion of the 70 centimeter band is 446 megahertz roughly, right? So what I want is the way that meter is reading right now would show, about 50 ohms, slightly more than that. And SWR is about 1.1. So that would be awesome. So let's see what we have. I turn this sucker on, and I'm going to go to 446. Should hold it away from me just a little.
So you can tune that to any frequency you want in the band?
Yeah, so I've got a little dial here I can go. It's got a band select, and then on any particular band I can move up and down with the dial. So actually it's not too bad. It is more like 75 ohms and SWR 1.5, which frankly that's not too bad. I could leave it. But then another way to check it out is, okay, what frequency is it really resonant on? What's the best SWR? So if I change the frequency back and forth, I'll find that the sweet spot for SWR 1.1 is, what's the frequency?
432.9.
Okay, so about 433 megahertz. Okay, so the antenna is tuned lower in frequency than we want. We really want it to be up at 446. So we're going to make it longer or shorter? Shorter. Who says shorter? Who says longer? You guys are good. So we're going to go shorter. So why don't you move that maybe a good inch?
Try that.
Okay. Try that. I can do the same thing. Let's tune around. Yeah, that's about right. We're at 446 megs. It's SWR 1.1 and impedance is 60 ohms. That's pretty good.
Can you try a little shorter?
No, I think that's good. So you have tuned your antenna. Let's give her a hand for tuning it. Okay,
Bob,
Barry.
yeah, okay, I've got a Diamond 30XA VHF and UHF antenna. How do you tune that? It's already pre-tuned?
You don't tune it.
You can't do anything with it, right?
I don't think most of the diamonds don't tune at all.
Correct.
What you see is what you get. Of course, they were tuned at the factory, right? So they should be good.
Depends on what day you tuned it. Monday? Friday?
Yeah. Barry.
Does that thing put out enough power that you worry about stepping on people on HF or UHF?
Yes and no. It's an interesting question because, yeah, you can hear the antenna tuner on an adjacent receiver. You'll start messing around with the antenna analyzer and you sweep it up in frequency, and all of a sudden you hear it go through your receiver. It's like, what was that? Yeah, that's me. I'm doing it. Now it's going to be a pretty small signal, so to probably be heard by your neighbors, but maybe not that far away. Other questions? Yeah.
I've been using my tuner in the past, and I get a low SWR, but I get a really wrong impedance. But SWR trumps impedance, so I want the low SWR, even though if it's the impedance is 72 ohms or something. Or do I want to try to find a compromise, get that impedance closer to 50 that the radio's looking for?
Well, they should be.
What's the balance?
They should be 1 for 1, right?
Well, you would think. But
So it's like if you have 70 ohm impedance in a 50 ohm system, that's turns out the SWR is just the ratio of that, so
Is that right?
70 divided by 50 is 1.4. Did I do that right? So you should be seeing an SWR of 1.4.
And reanalyze it, see.
Yeah, that's what's interesting. Take a dipole antenna. What's the dipole in free space? What's its ideal impedance?
Because it's right off the ground.
72.
72.
Yeah, it's right around 70, 72 ohms. So a dipole perfectly tuned to resonance in a 50 ohm system is going to have 72 divided by 50 is going to be its SWR. You want to think of them as 50 ohms.
If you have an external tuner, do you want to comment about where to measure the SWR? Between
Yeah.
the tuner and the transmitter, or the tuner and the antenna?
Well, yeah, I didn't include the slide on tuners. I mean, the whole idea of a tuner is, antenna tuner is it's not actually going to tune the antenna. It's a misnomer, right? But what it does is it accommodates whatever mismatch there might be on the antenna and the transmission line, but it makes sure that there's a 50 ohm impedance back to the transmitter. So it keeps the transmitter happy from the standpoint of the transmitter seeing 50 ohms, but it really can't change what's going on down the transmission line. So you might want to measure that SWR and know what it is, but typically you're measuring this side of the tuner and you're trying to get that 50 ohms to keep the transmitter happy, right? So you'll measure SWR on the transmitter side. Does that make sense?
The other thing you might want to comment on is what's the effect on the transmitter if you have high band SWR? In the old days, it used to be red transmitter tubes.
Yeah, in the old days, tube output tube transmitters had very robust